And as always, let us roll some tape. Hello, space fans, and welcome to Professor Britton's Wacky Universe. All right, space fans, welcome back to Astronomy 1020. As I've been mentioning, this is our last final week of lecture. Woo! We're getting to the finish line. I sent out a blast to all of my students last night, reminding slackers everywhere that this is the final week to get your stuff into me. I decided to give you all until Friday to get all of your labs and homeworks into me. We will not be doing a final exam next week because everyone opted for the I'd rather double my midterm than take a final option. That works for me too. Anyone who has issues with that, of course, can feel free to email me with a subject, I am dying to take a 100-point multiple choice test, and I will accommodate those people as needed. So far, I haven't had any emails like that, but I'm keeping a lookout.
You'll be expecting one momentarily after the class, okay?
Yeah, okay, right from you, Raph, right? Well, you guys haven't had the easiest go of it. It's a little more difficult to learn when you're sitting at home and there's puppies and kids screaming and stuff. It's not as easy as it is when you're just sort of sitting in class. It's never easy. That's
actually just me screaming.
But I'm glad to see so many of you here, including Juju. Man, nice to see you back in the game here. Don't forget that you guys have to.
That email scared everyone.
Don't forget that you guys have work to turn in to me. I've been a little behind on grading, and you guys have been a little behind on turning it in. Some of you have, anyways. So I'm just going to do a big smorgasbord of grading at the end of this week, and then we'll be done with it. So you guys think you can get that in by Friday? Anyone going to have troubles with that?
Nope.
Frank says, yep.
No, that's light work.
Okay. Okay. Talk to me if things are different. Okay, so what are we going to do today? We're going to leave relativity behind, but not exactly. We're going to need to use some of our lessons from relativity, and we are going to kind of carve out the end of chapter 17 on nuclear fusion and dive into the death of stars. The death of stars will probably take us into Thursday's final lecture. All right. So what I would like you guys to do is, oh, by the way, today's lab, and since I haven't mentioned it yet, is on a legendary case study in astronomy called the period luminosity relationship. We are going to be studying a special class of stars known as Cepheid variables. These are blinking stars. They pulsate, and their brightnesses change. And we can use this through trickery in mathematics to determine the distances to galaxies, other galaxies. It's going to be cool. And it's a fun, quick little lab. For now, what we want to do is we're gonna kind of get back into stars where we left off over a week ago. And sometimes what I like to do with chapter 17 is summarize all of the different types of nuclear fusion in stars into a convenient table. It is a crude method of learning, but I have to say it does digest many, many words of chapter 17 into a simple and easy to read graphic. So I'm going to kind of reconstruct that table, and we're going to step through the boxes, and that will help me keep my thoughts organized, and hopefully it'll make some kind of sense. So let's go to speaker view, and let's zoom in on me. And I want to see if you guys can find in your notes that day when we made a table that looked something like this. We had columns for our different stellar mass ranges, okay? And then we were going to walk through the different stages of their lives, starting with when they fuse hydrogen into helium, and then looking at subsequent epochs of nuclear fusion. To do this, I think we're going to need one column on the left for the mass range of stars. We'll need a column for their main sequence phase. a column for red giants, a column for supergiants, and one for the death of stars. So you guys actually probably already have this table partially constructed. If you are a note-taking type of person, you can flip back through it. This is the mass range of stars. This is the main sequence phase of stars. I'm just making sure you guys can read this. This is the red giant phase. This is going to be the supergiant phase. And then we're going to have a column for the death of stars. And this is going to be a crude but effective summary. Hold on, let me get the blinds.
Oh,
Okay.
yeah.
So class, why don't you remind me what you have learned, what things that you know. Hold on a second. My lighting team took the day off, so I'm going to have to do this. Class, tell me about the 3 different classes of stars that we have. We have high, medium, and low mass stars. And I want to see if you guys remember what the differences are between a high mass star, an intermediate mass star, and a low mass star. You guys remember anything about stars? Oh, geez. Guys, I had like 4 cups of coffee this morning, so I am burning like a nuclear fusion bomb, and I need you there with me so that I don't feel lonely sitting here drawing notes on my apartment chalkboard.
Yeah, I think I could speak for the rest of the class in answering no. We don't know or remember anything about stars.
High mass stars are higher up on the main sequence,
Yeah, higher up on the main sequence.
and then
but-
low mass are lower.
but- So, okay, you know what? I think we need to, it's always good to start the day with a graph or a graphic or something. Let's tiptoe through the PowerPoints here until we can find ourselves a nice HR diagram. The mass ranges of stars, they go well beyond just the main sequence, but we focus inordinately on the main sequence for a couple of different reasons. The first is that although this little cartoon doesn't show it, this is a wonderful information graphic. It really tells you a lot of information if you're a new learner to HR diagrams and stellar physics. But we focus inordinately on the main sequence because pound for pound, most stars are found there. And this is just because stars always begin their lives in the exact same way. They start by fusing hydrogen into helium. Why? Because the universe is mostly hydrogen. I mean, 98% of the universe is either in the form of gas or stars, and those gases and stars have more or less the same composition. You guys are supposed to know what that composition is. 70% hydrogen by mass, 28% helium by mass, and 2% metals. And that means when stars first assemble, they're basically big balls of hydrogen. And that means that they're going to start fusing hydrogen into helium. Believe it or not, pound for pound, this is the most efficient form of nuclear fusion. Let's go back to our lecture on stars, the intro lecture on stars, and let's look at a real HR diagram, not that cartoon shit they're showing you in the textbook here, but one that's taken by a satellite like the Hipparcos satellite. Oops, sorry. I thought I was onto something there. Here's a real HR diagram taken by the Hipparcos satellite, F565. You can see that each one of these dots is a star for which the scientists have taken 3 pictures, a picture with red glass, a picture with green glass, and a picture with blue glass, and they've plotted their color, which is a cheat for temperature, versus their absolute magnitude, which is a cheat for luminosity. And when you plot their positions, I don't know how many dots are here, I'm guessing this is maybe a few thousand. I have hard time. I was never good at that game. How many peanut M&Ms are in the jar? I could never do that game well. Some people are good at that sort of thing, but I guess there are a few thousand here. And I'd say it looks like 70, 80%, maybe even 85% of the stars are found along the main sequence. And you'll notice it's not perfectly diagonal. It's got some interesting wiggles here. Now, that means we focus on the main sequence because most stars are found on the main sequence. And this is what is called in astronomy a selection effect. The lives of stars are not totally dissimilar in phases to the lives of humans, right? Humans are born, they go through a little adolescent phase, they have a sort of adult phase, and then they go into an elderly and senile phase, and then they die. And all of this is true with stars as well. If you were to take your entire life and take a Polaroid picture of yourself every day and put it in a box, and you lived for 100 years, how many Polaroid pictures would that be? That would be what? 365 times 100, right?
Yep.
So that's about 36,000 Polaroid pictures. Not as many as you'd think, right? If you then shuffled that box up like a lottery game and you reached your hand in to grab one of those pictures, the chances of you finding the photograph of the first day you were born or the last day before you died are pretty low. You're more likely going to find a photograph somewhere in the middle when you're in your 20s or 30s or 40s or 50s. And that's kind of what this main sequence is all about. When we take a snapshot of the universe, we catch stars in their sort of main adult phase of their life. And that's when they're fusing hydrogen into helium. So because hydrogen fusion takes the longest time, that's why we find so many stars along the main sequence. Now, what's good about that is only along the main sequence is there a tight correlation between a stellar mass and its color or spectral type. Once stars go and turn into red giants or supergiants, the mass ranges get a lot more difficult to constrain. Like, think about one of the most famous stars in the sky, Betelgeuse, right? If you guys go and you just type Betelgeuse into Google, and we look at some of its stats on Wikipedia here, I want you guys to notice the tolerance or the uncertainty in the estimate of Betelgeuse's mass. If you guys can see over here, the part that I have highlighted, our most recent research, which we can link to this paper by Nielsen here on the archive if we want to, weighing Betelgeuse, measuring mass of Alpha Orionis from stellar limb darkening. Ooh, sounds like a juicy afternoon read, okay? Anyways, if you cut through all that crap, you discover that Nielsen's best estimate of the mass of Betelgeuse is 12 solar mass units, plus or minus 5 solar mass units. So Betelgeuse could be anywhere from like 7 solar masses?
It can be anywhere between like 7 to 17.
Yeah, exactly, right? So there's because Betelgeuse is a red giant, because it's not on the main sequence, and because it's also not part of a binary. Remember, we did a lab where we learned that the purpose of binary stars is to measure masses. Betelgeuse is the worst possible candidate for estimating mass because it's just one single star and it's a super giant star. So not only do we have no like orbital dynamics for it, but we also, not being on the main sequence, you kind of lose track of what the mass is. So that was a lot of yapping, but if you followed me, the point of the yapping was high, intermediate, and low mass stars are not just for the main sequence, but when stars are on the main sequence, we have a much better concept of what their masses are. Okay, so help me fill in the boxes then, class. What are the ranges for high, intermediate, and low mass stars? Who remembers stuff?
Hope.
Sorry?
I said Hope.
Hope?
Yeah,
Nope.
Hope.
Oh, I'm sure Hope knows.
Oh, I see. Hope. The student Hope. Yes, Hope. We're calling on you. What do you think, Hope?
Yes. No, look, he knows. He knows.
My plan worked.
Okay. Come on, I'm sure one of you guys remembers the ranges. Do you just? I was hoping you'd have your notebooks there with a chart. This proves that I actually did this. It's not a figment of my imagination. Did anyone take notes?
Oh yeah, mine are like.
Julio, wait, Julio, you said I said your name wrong the other day. Can you help me then?
Yeah, it's pronounced Julio.
Oh, Julio. Isn't that what I said?
No, you said Julio.
Wait, what?
Yeah. Wait,
The differentiation in the H and J sound.
Wait, what? Wait.
Oh Christ. Okay.
What?
All right. Wait, one more time then. Help me get it right. I can only get it right if you help.
There are two versions of saying my name. There's the legal one, Julio David Samayo Zice, and the one that I give white people, Julio.
You better give me the white people.
Yeah, okay. You know what? You're good. I'm just trying to find the chart.
It's not that I want to suck. It's just that I do. Okay.
20 years.
Wait, what's the difference? Wait,
Take
what?
one, white people.
Oh my God.
Okay, look. To the artist formerly known as Julio, what are the mass ranges of stars? Okay.
God damn.
Anybody, come on. Wait, do you know it?
All right.
Talk turkey to me. Oh, he just muted himself. He's out. Okay.
All right. I'm still trying to find the chart.
Riker, you got a chart? Who's got a chart?
I'm looking. I don't think I have a chart. I know you mentioned it, but I don't think I have a chart. I'm poor on notes.
The thing is,
One of us
that I
must
never
have,
made a
one of us
chart.
must have drawn it.
we've taken so many notes that I have no
Yeah.
idea where my chart would be.
That means
Oh,
you're getting
God.
good value for your money. You see, the density of notes is high. You can't say,
No.
I'm not complaining.
O,
I'm
B,
just
and
saying.
some A.
okay, those, Tim,
Can I
those are
sit
the
here and start taking guesses?
Tim, those are the spectral types, but I'd say A is more intermediate. Okay, why don't I fill it in for you then, students? I guess I'll have to do my job, okay?
Hey.
Solar mass units to 100 solar mass units. That's high mass stars.
Oh, I found it. I found the chart.
Great job,
Yeah, Morgan?
The answer's 2
Yeah,
solar mass.
Morgan with the charts?
And then,
Juju quit. Juju just quit. He's out.
oh man. Okay.
My internet says it's unstable.
A tenth of a solar mass to 2 solar masses. That's okay. It's all being recorded. Okay, Tim, since you seem to be chomping at the bit there, do you want to help me fill in the spectral types of these stars? What spectral types do high mass stars comprise or are composed of? I don't know.
O or B.
Yep, it's got to be O's and B's, and I'm putting them in blue. How about our intermediate class?
A,
Spectral
F, and
types?
G.
A, F, and G.
Remember, G is like the sun. What's the mass of the sun?
Oh, G
One
is a
solar
low
mass.
mass.
Yeah.
G is a low mass.
Yeah, I'm going to put A in blue. Note my color choices here are highly symbolic, okay?
So G, K, and M are in the low.
What color should I make G? What's the peak sunlight, what's the peak wavelength of the sun's emission? Does anyone remember? A 5800 Kelvin black body, what's its maximum wavelength of emission?
Red.
Anakin.
Yeah, and again.
Pardon?
Green.
Yeah, 500 nanometers. Very good. All right. Impressive. And then we got K's and M's as well. So those are red, right? Ooh, my red marker looks juicy today. I like it.
Like blood.
It's great.
Okay.
Okay. Now, you know, I want to walk you guys through a concept here. We're going to look at some charts. Let's talk about we talked about protostars at some point, right? What the hell is a protostar? Anyone know what a protostar is?
Isn't it?
What's the difference between a star and a protostar anyways?
So a protostar is a star with the protosphere?
No.
Isn't a protosphere
I mean,
spewing stuff
Right.
outwards?
No. I mean, it sounds so good, but it's not. Wait a minute. Hold
Oh,
on,
it's
I have a lecture
proton.
on.
It's at
Proton.
the end of the star's lifetime, right? When
Isn't
it's
it
given
too
some
small
hours.
to maintain hydrostatic equilibrium?
No, protostars do maintain hydrostatic equilibrium. So, and it's not small because protostars can be big as well. I
It's
think
not?
this is. I think this is the slideshow where I have protostars. Let's take a look at a model of a protostar just to see what the sun would have looked like when it first formed. You guys will remember that we actually have the ability to image protostars by using infrared telescopes such as the Spitzer Space Telescope. If you've never heard of this telescope before, I made a brief mention of it before. The Spitzer Space Telescope is sort of like the Hubble Space Telescope, but for the infrared. It's a telescope that's in a space orbit around Earth. Unlike the Hubble, which looks at mostly visible wavelengths, the Spitzer Space Telescope starts at a micron and goes up into the infrared. And remember that infrared wavelengths have the ability to penetrate through that pesky dust, which blocks our view of the disk of the Milky Way. And by peering into the hearts of these giant molecular clouds, like this one here, the FU nebula, okay? By peering into the cart of the giant molecular clouds, we can see newborn stars forming, and they give off a lot of light, especially in the infrared. You can see the main protostar is here, surrounded by a black dusty disk. This disk is the material that will later condense to form the solar system, or a similar solar system. In fact, if you could zoom in and see that with higher resolution, let's get the help of our weed smoking artist friends here.
Hey.
If you could fly into that Proto-Solar Nebula, as it's called, you'd probably see a picture that looks something like this. Let's see if I can get an even jazzier one. I think I've got a couple of jazzier pictures here. Oh, I like this one right here. This slide, F533. This is something like what that dark disk of material would look like. It would be a swirling disk of dirty hydrogen and helium gas, some of which is coalescing into planets, and most of the material would be concentrated at the center where this protostar is forming. If you were to look at a protostar, it would look exactly like a normal star. It would be a big, brilliant sphere that emits tons of light across the electromagnetic spectrum. It would be a very hot black body. In fact, protostars tend to look even crazier than the stars they will later become, because protostars are often accompanied by these very violent magnetic jets that are basically funneling plasma along the polar axis of the star and rocketing those charged particles into the surrounding nebulae. That's why when you look at these images of what we call propylids or protoplanetary disks, you can see they look like little tadpoles. Can you guys see my screen okay here? You guys can see these images, right?
Yeah.
Yep.
All right.
Yes, it can.
Those little tadpoles are from the magnetic jets just shooting plasma into the surrounding interstellar medium. So I ask my question once again, class. What is the difference between a protostar and a star, besides the magnetic jets?
Protostar's not quite a star yet.
Why not? That's kind of the right answer, but why not? What is our definition of star?
Is it not? Is there not fusion in the star yet?
Booyah, that's the answer. Remember that our working definition of a star is ball with fusion. And the only difference between a protostar and a star is that the protostar is a ball without fusion. Why is there no fusion? Its
Not big enough yet.
central temperature is not high enough. Now, you might be wondering how we know this. We know this from two different directions. One is through simulations and computer modeling, probably done at the Los Alamos National Laboratory, among other places. But another way is by plotting the positions of newborn protostars on the HR diagram and trying to understand what's happening with them based on their temperature and their luminosity and their radius. At its basic design, an HR diagram is just a plot of two quantities. It's a plot of temperature on the x-axis and luminous output on the y-axis. And if you think about it, anything that's even remotely like a black body, anything that has temperature and emits light, can be plotted on an HR diagram. Hell, you could plot your own body on an HR diagram. You are a human. Your average temperature, 96 Fahrenheit, translates to 310 Kelvin. And you pump out about, what did we calculate in the earlier lecture? 400 watts per square meter is the typical luminous output of a human being. So if I tried plotting myself on an HR diagram, I would be way the hell over here on the left, near 300 Kelvin. Kind of hard to draw with this. So there's 300 Kelvin. And I'm guessing that my total luminous output is 120 watts, which is a lot less. Here, 120 divided by 4 times 10 to the 26 is 10 to the minus 25 solar luminosities. So if I were to compare myself to the luminosity of the sun, I am 25 orders of magnitude less luminous than a star, okay? However, these quantities could be plotted on an HR diagram, and I guess that would put me somewhere, boop, right there, okay? That's where I go on an HR diagram. Now, with that in mind, let's go ahead and let's try to plot a typical protostar on an HR diagram. Bear with me here, and let's see where we end up. Groups of astronomers have been doing this for more than 50 years, and this is a cartoon of what they discover. 56. When a star first begins to form from a giant cloud of gas, it's basically found sort of where you are in an HR diagram, way over to the right, where it's cold, and way down where it's not luminous. But as a star begins to contract, you can see that as the star shrinks and then forms a protostar, its temperature goes up because contracting gases makes their temperatures rise, and its luminous output increases. But stars kind of go through these interesting wiggles on their journey towards the main sequence. First, they contract, and that shrinks their amount of luminous output. And then they go from convection towards radiation as they become ionized. And eventually, they kind of migrate their way down to the main sequence. And that's where they begin their lives as bona fide stars fusing hydrogen to helium. That's where we begin our table, okay? So, on the main sequence, and I've done this before, we fuse hydrogen into helium. And y'all are supposed to know the different types of nuclear fusion reactions that these stars undergo. Let's start with low mass stars like our sun. What's the name of the nuclear reaction sequence that produces energy in our star?
Proton chain.
Thank you very much. I'm gonna use its technical abbreviation, the PP chain, okay? And here we go. So this is proton-proton chain. And in the proton-proton chain, 4 hydrogens make 1 helium plus 2 gamma rays. Do you guys remember what nuclear reaction sequence high and intermediate mass stars use? It's not the PP chain. Wow. Shucks, I thought y'all were the type of folks that remember things. But I guess we got to just keep going. You know that movie, what is it, Memento, where the guy has amnesia every day, and so he has to tattoo what happened the day before on his body so that when he looks at his face in the mirror, he'll remember, like,
Using it with Groundhog Day.
oh yeah, no.
Oh,
Groundhog Day is like, that's like what it's like to be a teacher, okay? Every
I would
semester.
have just wrote on the mirror.
Are you suggesting that we tattoo our lecture notes on our bodies?
I mean, that was the implication, yes.
I would have just wrote on the mirror. That seems so much easier than
I'm
tattooing your
respectfully
face.
gonna pass on that, but thank you. Blue, you're in.
Okay, all right.
Fear of needles that extends to my face.
All right, then
I'm
let's
good.
look at my slides instead, since you refuse to get the nuclear reactions of stars tattooed on your body. You know,
I already regret the last tattoo I got.
it's
I'm not
called the
gonna do it.
CNO cycle. F594. The CNO cycle actually uses metals, the 2% metals, to forge hydrogen into helium. At high temperatures, stars prefer this nuclear pathway over the proton-proton chain. Why? I don't know, man. That's a little over my pay grade. You got to ask a hardcore nuclear physicist the answer to that question. But the carbon, it's very confusing because the name of the reaction is carbon-nitrogen-oxygen cycle, and yet these elements are only peripherally involved. The real purpose of the reaction is to take 1, 2, 3, 4 hydrogens and slam them into an alpha particle, although I will say they do release 3 gamma rays. Now, I walked you through this once before, so I'm not going to do it again because that would be foolish. But we'll write it down here on our boards, okay? We have the CNO cycle. CNO cycle. And the summary of that is that 4 hydrogens fuse into 1 helium plus 3 gamma rays. You'll remember that I made kind of a big stink about the fact that the CNO cycle is 50% more energy efficient, or, well, yeah, 50% more energy efficient or energy yielding than the proton-proton chain, resulting in a much shorter lifespan for the formations of stars. Hey, I want to play a little game with you guys. You know, talking about stars should be interesting, but sometimes you can get a little seasick from it all. Let's compare the time it takes a star to form to its total lifespan, okay? So let's look at this picture. This picture shows how long it takes stars of different masses to form. 60,000 years for an O-type versus 150 million years for an M-type. And let's compare it to their, so that's slide 57. I want to go back and forth between slide 57 and 3. So I'm going to write those numbers down in my corner here. So let's play a little game together to try to figure out how a human being's life compares to the lifespan of a star. Just bear with me here. I'm going to explain what we're doing. Slide 3. Okay. Let's talk about high mass stars like O stars. How long do they live for? How long? Oh, sorry. Let me try that again. How long does an O-type star spend fusing hydrogen into helium on the main sequence?
Can you say that again?
Sure. I'm basically asking you to read this number, but say it in English. How long does it take an O star to go through its entire supply of hydrogen fusion?
10 million years.
Thanks, Nathan. 10 million years. Now compare it to slide 57. How long does it take forming?
60,000.
Okay, so let me see if I can annotate this because I don't want to mess up what's going on my board. I'm trying to do 60,000, right? 60 times 10, I hate this kind of, whoa, sorry, something's not working here. So I'm trying to do 60,000 years, and I'm trying to divide it by 10 million years, right? What's that ratio give you? Do it on your calculators.
0.06.
You showed up.
I got 6 times 10 to the minus 3.
6 times 10 to the minus 3.
Right? Okay, how does that compare to a human being? Let's see, how long do we spend forming? 9 months?
9 months.
So that's
Could you imagine
0.75 years. And how long do we live
60,000
for?
years? That's rough.
85.
25,
Okay.
80 years.
75.
So what's our, what percentage of our life do we spend forming? 9 times 10 to the minus 3. Not too bad.
Yeah.
That's kind of, isn't that weird? That's sort of comparable. Okay, so that's for an O-type star, right? In fact, what I should have done here is I should have made that blue. Okay, oops. All right, why don't we compare this to an M-type star? An M-type star is 150 million, right?
Yep.
Divided by, what's the typical lifespan?
Blue is probably not the best color for that.
Yeah, I know. Anyways,
Now it's even worse over there.
what do we got?
100 billion.
100 billion. So let me go to slide 57 where I've got some blank space. Oh yeah, blue is a terrible color. All right, so hold on. I'm still getting used to writing on this thing here. Whoop. Oh, so 100 billion. Anyways, do the math. What do you get?
1.5 times 10 to the negative 4th.
So 2 times 10. So what would you say? Are we more like an O star, or are human beings more like a M or a K star, a K or an M star?
In that
more
one
like an O
aspect,
star.
I would say O stars.
Yeah. So O stars are kind of comparable. They spend. It's kind of interesting that's strictly numerology. I don't want you guys starting to think this is like one step away from astrology and smoking your peace pipe for breakfast. All right, I don't want you to
like
think
one of those
this is
Facebook
hardcore
quizzes.
science.
What kind of star you are.
Wait, what's that, Zach?
I said this is like one of those Facebook quizzes where you put in all your information and you see what kind of star you are.
Yeah, I know. This is pretty bad. Nice to see you with us, Zach.
Hey, good to see you guys too.
Zach is here.
Yeah, he's in the house. The point that we're trying to make, though, is the ratios are not too dissimilar. Okay, let me get rid of this before any professional scientist sees what I just did there. Oops, hold on. How do I erase all this stuff? Okay, good. All right, so if we're trying, but you know, a human lifespan is something that we can understand, and stellar lifespans are quite a bit longer than that. So we need some kind of analogies so that we can sort of make sense of all this madness. Of course, stars begin their lives undergoing fusion, and then they look like one of these three giant spheres here. Where are our stars of different mass ranges? Here we go. Okay, so on slide 74, you can see this is what a star looks like when it's undergoing its main sequence fusion. These stars are in hydrostatic equilibrium. That means there is a balance between the gravity squeezing in on the star and the thermal pressure pushing back on the star. But the thermal pressure, of course, is being supported by the nuclear fusion, which is spitting gamma rays out into that star. Not all stars maintain hydrostatic equilibrium, as we will see in our lab today. Let's imagine what happens as a star, you know, our sun today is halfway through its lifespan. Our sun, I think, can fuse hydrogen to helium for 10 billion years, and we're about 5 billion years old, so we're halfway through our lifespan. What would it be like if we could project the future of our own star forward to that day when the hydrogen fuel is starting to run out? Now, before I do this, I want to show you guys an advanced graph. I want to pull the wool from your eyes, and I want to use the internet here to show you guys something a little more intense. Let's look at the mass profile of the sun and see if we can get a graph for that. A mass profile means how does the mass change with radius? Here we go. Obviously, a star is not, well, this is its density profile. Let's see what this one looks like. A star does not have a uniform density. Shoot. Why can't I click on this graph? Oh. These are the graphs I want. But what? Can you guys hear me? Is my internet okay? I'm starting to get the heebie-jeebies here.
Yeah, I can hear you.
I can hear you. I
Hey.
can see what you're doing.
I want. Am I on image search? Yes. Tools. Wow, it's like nothing is working right now. That's why I'm surprised you guys can still hear me. Okay.
Yeah. I'd
Dan-
say your internet is down, obviously.
But if my internet is down, how can I be video chatting with you guys?
Well, that's why I say that's why I'd to be like, well, I mean, obviously.
Well, I mean, every now and then there's a bit of a lag. I don't know if that was me though.
You're a little laggy. Okay, you know what? I can't get. I'm not entirely sure why it's doing this, but I guess I can explain the purpose I'm trying to. A star is not a uniform ball. It's not a block of wood. It gets denser as you go in towards the core. And I believe the inner core of the sun, it comprises about 15% of a star's radius, but it does not comprise 15% of a star's mass. The inner core of a star is roughly about half of its mass. That is to say, if I look at a picture of the sun, you failed me, internet. This illustration looks like the core is just a small fraction of the sun's total matter, but the core is probably a little bit bigger than this, and it packs about half the mass of a star into there. Now, suppose I consider the sun is one solar mass, right?
Yes.
Suppose I just stripped away the outer convection zone and radiation zone of the sun and exposed the nuclear core. That lump would be a ball of gas and fusion that was 0.5 solar mass units. What spectral type of star would that correspond to? What's the spectral type of a star that has a mass of 0.5 solar mass units? The answer is right here on my slideshow. You can just read it off the slide. Oh, I like your background, Zach. How come everyone's background looks better than mine?
It would be approximately about here.
Oh, damn, that's jazzy, Riker. I like that. Nice moves. So a spectral type, wait, so let's see, can we collaborate here?
Spectral type K.
Yeah. Spectral type K. Ooh, look at that. Okay. Wow, Riker, that's cool. I don't know how you did that, but we'll keep doing that, okay?
Under the annotate, there's a little thing called arrow.
Oh, okay. And then it'll have your name automatically embedded in it?
It'll put my name on it automatically.
The point that I'm trying to make, students, is that in a way, there's a star inside my star. The sun is like a spectral type G star, and in the core, that's like the equivalent of a K star just in the center of your star. But one should ask themselves, just how does the core of a star maintain hydrostatic equilibrium? So for this, I'm going to do a little bit of drawing over here. Okay, so imagine what it's like if you could look inside the core of the sun towards the end of its 10 billion year lifespan. So I'm going to draw a ring here that represents the inner inert helium core. Okay? And I'm going to surround this with a ring of hydrogen fusion. And this is what is called hydrogen shell fusion. And surrounding this is going to be a purple zone of hydrogen, which is not hot enough for fusion. So these dots here, they represent cooler hydrogen that's not capable of undergoing fusion. So this is cool hydrogen. Obviously, the temperatures could be in the millions of kelvins, so cool should probably be in quotes there, okay? How many times heavier is hydrogen than helium? This is a question I'd expect you to know the answer to. Helium is how many times heavier?
4
Pardon?
times.
4 times, right? Because there are 4 nucleons compared to 1 nucleon?
Yep.
How many times heavier is stone compared to water? Does anyone from my astronomy 1010 class remember the density of stone?
No.
What's the density of water?
1.
1 what?
One density unit.
No, F you.
Yeah, 1 unit of density.
What units do we measure density? You got 2 options. If you're saying 1 is the density of water, I'm okay with that, but that means you're talking in particular units, and I need you to know what they are. It's grams per cubic centimeter.
Grams?
I got time for your shit, okay? 1 gram per cubic centimeter is the density of water. What's the density of rock? Someone who took my solar system class is supposed to know this. Anakin.
I did take it. I don't remember it.
The density of
Maybe
rock is
5.
5 is like the density of Earth, Anakin. 3 is
Okay.
the density of rock. All right, look, I'm just trying to make a simple point that, sorry, someone just went over somebody's heads, all right? So the density of stone is 3 times greater than that of water, right? The density of helium is 4 times greater than that of hydrogen. What happens if you drop rocks in water? They sink to the bottom of the river. So a very similar thing is going to happen in our star as it fuses hydrogen into helium. At 4 times the density, all of the helium is going to sink to the center of the star, and the hydrogen that is fusing will remain wrapped around it like a Tootsie Roll or a Tootsie Roll lollipop. It'll be surrounding on the outside. The question that we have to be asking ourselves in that case is,
How many licks does it take to get to the center?
yeah, exactly. That's the purpose of this whole class today, is how many licks it takes to get to the center. All right, no. The purpose is, if that's the equivalent of a K-type star, but it's not undergoing fusion, how does that star maintain hydrostatic equilibrium? Because all of the gamma rays this star is producing, all of the gamma rays are heading out upwards into the sun to help the outer envelopes maintain hydrostatic equilibrium. How does the inner inert core not collapse into a black hole under its own gravity? What keeps this thing from crushing itself to death? Now, I don't know if I told, does anyone know?
Is it like not dense enough or too dense?
It's too dense. That's the answer.
Yeah, okay, it's too dense.
Okay, so we have to have a talk about degenerate gases, okay? Degeneracy is something that I've
I'm
been
very common.
all my life. Here,
Very
let's
firm grasp on degeneracy.
That's too high. I need those, where are those little physics Java apps? Let's get our gas properties up. Now, I'm going to use this simulation here for perverse, degenerate purposes. Okay. A normal gas obeys the ideal gas law. And in the ideal gas law, let's get, you know what? Let's get some light species in here too. Let's put some hydrogens in there. Maybe the blue pellets are helium and the red pellets are hydrogen. A normal gas obeys the ideal gas law. And during the ideal gas law, there's a relationship between temperature and pressure and the density of particles. And although this gas is pretty well packed, I would still say that the interatomic spacing, the spacing between the atoms, is still greater than the size of the atoms themselves. Not so when you hypercompress a gas at the center of the star. First of all, let's add some gravity. Here goes my gravity bar. Boom. And now I'm going to begin to crush my gas. Sorry?
Sorry.
Oh, that's just some chatter. Okay. Here we go. I'm going to crush my gas. Crush. Oops. Let's get the lid
You
back on.
blew the lid off.
Let's get the lid back
And
on.
all
Let's
the air
use
got out.
light species. This is sort of what a degenerate gas looks like. A degenerate gas is one in which you've packed the atoms so tightly together that the spacing between the atoms is comparable to the size of the atoms themselves. When this happens, the ideal gas law actually kind of breaks down, and the gases enter a stage called degeneracy. It's basically where the quantum states of the electrons begin to overlap. Now, I don't know if you ever heard about this thing before, but in quantum mechanics, there's this concept called the Pauli exclusion principle. And no two electrons can have the exact same set of quantum numbers. They can't have the same energy, spin, angular momentum, and direction of angular momentum. And this is one of the reasons why in your chemistry class, if you guys took a chemistry class, you remember that you can put two electrons in each energy state, one spin up and one spin down, and then you've got to move up to the next energy state because you can't have overlapping electrons. Basically, the stupid version that doesn't involve quantum mechanics. Let's stupefy the Pauli exclusion principle. Let's pretend that these are electrons. They can't overlap one another. Like they can't completely occupy the same space. Anyways, okay. Degeneracy pressure is so intense that it can actually support the weight of your star. So the inner cores of stars are actually degenerate, and that's what keeps them from collapsing into a black hole. By the way, I also we suspect that the inner components of gas giants like Jupiter and Saturn and Neptune, these must be degenerate as well. I don't know about the center of Earth. There might not be enough mass to create degenerate matter there. And degeneracy pressure, electron degeneracy pressure, can support the weight of your star for a while. But when a star completely runs out of fusion, the core of the star begins to shrink. And weirdly, this is what turns the star into a red giant. Your inert degenerate helium core begins to contract, constraining all of your fusion to a thin little shell. And this thin little shell of fusion goes so bonkers that it puffs out the outer envelope of your star into a red giant. We've now entered the red giant phase of a main sequence star. And eventually red giant stars, let me see if I can show you a picture here. I want to go back, sorry, I'm looking for a particular slide. Here we go. When our own sun starts to turn into a red giant, as you know, its temperature will cool and its radius will swell right up into the point we call the helium flash, where helium begins fusing inside of stars. I think I actually did most of this already with you guys, so I don't think I need to talk about this quite as in depth as I'm used to. So if we were going to continue to fill out our charts here, all stars, high, medium, and low mass, all eventually hit a point where they can undergo helium fusion. And helium to carbon fusion proceeds by, you guys remember the name of the reaction? How do we fuse helium into carbon? Nothing, huh? Nothing?
Add a atom.
I don't even understand what that.
No.
I don't even understand what you just said.
God.
We had a homework problem on it. What atom do you get if you smash two helium nuclei together? What atom has 4 protons and 8 or 9 neutrons?
Beryllium.
All right. So we fuse 2 heliums into beryllium, and then we fuse beryllium and helium into carbon. That's called, where is it here? Triple alpha process.
Bless you.
Helium's fused to beryllium, beryllium and helium's fused to carbon. Let's write it down. The triple alpha process. Now, let's see. 3 heliums form 1 carbon plus 2 gamma rays. We did all this, right?
Yes, we did.
Okay. I don't know why I'm going over the same stuff again. It's probably not what I should be doing with my day here. Okay, I have an adult question. How does the energy efficiency of the triple alpha process compare to the energy efficiency of the proton-proton chain?
Well, aside from the
Same, isn't it?
It looks the same, but it's superficial, Nathan.
'Cause they're
Okay.
both pumping out 2 gammas, right?
They are pumping out 2 gamma rays, but each reaction requires a different quantity of mass. I need to show you an adult slide that is not easy to understand. In fact, I'm probably not going to do a great job explaining it, but I'm going to try. It's called the nuclear binding curve. This is one picture of it. There's kind of cooler pictures on the internet if my
Nope.
internet works. The binding energy of nuclei. It's got a couple of different names here. I like this one here. This is from the Wikipedia page on nuclear binding energy. I just want to get that graph. Sorry, I just want that graph with a white background. There we go. All right. So I want you guys to look at this. This is a sort of legendary graph in nuclear physics, trying to explain how much energy you release by fusing one type of nucleus into another. Okay. Now, you guys will remember that there's nuclear fission and there's nuclear fusion. What's the difference between fusion and fission? And you have to know that before I can talk to you about this.
Putting atoms together and tearing them apart.
All right, cool. So if you guys look over here, when I fuse hydrogen into helium-4, you can see I release the greatest amount of binding energy per nucleon, whereas fusing helium into carbon looks like it's the same amount of energy, but it's because it's 2 gamma rays, but it's not the same amount of energy if you measure it per nucleon. Let's think about this. If you fuse
1/7, right?
Huh?
It's like 1/7 of the output from the.
Or maybe even 1/14. And here's why. When you fuse 4 hydrogens into 1 helium, that requires 4 nucleons, right? But if you fuse 3 heliums into 1 carbon, that's 4 times 3 or 12 nucleons. So 12 nucleons is like, that's 3 times as many particles involved. Now, if you're inside the core of a star, sorry, I'm trying to get my eraser here. What this means if you're inside the core of a star is you're going to crunch through your mass much faster during helium fusion than you will during hydrogen fusion. And that's because if you think of each reaction as you take a little bucket of hydrogen atoms and you convert it into helium, each little bucket of helium that you convert into carbon is 3 times more matter. And that means stars cannot live as long as red giants as they do on the main sequence. Helium fusion just requires more mass. And it looks like it's giving the same number of gamma ray energy outputs, but it's requiring more more kilograms of material per reaction. And for that reason, when stars eventually do become what are called helium-fusing stars, first of all, they become unstable and they pulsate. They occupy a region called the instability strip on the HR diagram. This is where our Cepheid variable stars come from that we're going to study today. And for a while, they kind of return to normalcy, but eventually all of that carbon starts to deposit as ash in the center of your star. And eventually, I should have a better picture of this somewhere, but eventually your star kind of goes through a cycle that looks like this. Function F584. Eventually, your star goes from having non-fusing helium to helium fusing, and eventually it starts to pigpile a bunch of inert carbon into its core. And look at what happens to our star in the HR diagram, the weird throes that it goes through as it goes through its 3 stages of red giantness. First, it's a subgiant and its radius starts to grow. That's where the sun will swallow up Mercury and Venus and maybe even Earth. Then the helium fusion kicks in and it returns to hydrostatic equilibrium, becoming a helium fusing red giant. But then as the carbon starts to build up inside of a star, it starts to swell again into a double shell fusing red giant. And basically that's when the star is going to end its lifespan. Low and intermediate mass stars will never get enough matter to fuse carbon together. I think the fusion temperature of carbon is 600 million Kelvin, and under 8 solar masses, you just don't have enough matter to fuse stars into their final stages. So, after the triple alpha process, oh yeah?
I thought that some stars went up to iron.
Those are only this, so that's the whole purpose of my chart here, Nathan.
Okay.
These stars can go up to iron. These stars here can only go to carbon.
Carbon.
So
Gotcha.
carbon is the final state of both of these types of stars. And they go directly to their death throes where they form 2 structures. They form a planetary nebula and a white dwarf. By the way, our entire class, Zach, the answer to what pages you need to print for your lab are go to the blackboard, go to the period luminosity relationship. Actually, I should do that too, but I'll tell you that at the end of our lecture today. We're going to spend our last lecture looking at the details of all of these types of things. Now, if you're a high mass star, high mass stars can go through additional layers of fusion. And because I've got to find a way to condense this, let's look at the internal structure of a high mass star as it goes through various stages of its life. High mass stars undergo triple alpha process as well, but they are capable of doing additional fusion reactions with carbon. Now, they go by various technical names. One of the first ones is called helium capture. Now, this has got something to do with nuclear physics, but damn, nature just loves an alpha particle. There is something about 2 protons and 2 neutrons that is just a very inherently stable configuration. The strong force really likes this combo. So helium nuclei become bullets that smash into heavier metallic elements to build up heavier elements. Carbon gets whacked with helium to make oxygen. Oxygen gets whacked with helium to make neon. Neon gets whacked with helium to make magnesium. And then the big boys start to react. Carbon and oxygen whack together to make silicon. Oxygen slam together to make sulfur. Silicon is where beach sand comes from, right? Silicon slam together to make iron. Most of the terrestrial planets have iron as their core. No surprise there. Iron is a special nucleus in nature. It's sometimes referred to as a magic nucleus. there's a kind of perfect harmony between the electrostatic repulsion of all of these 26 protons and the strong force trying to bind it together. If you look at the nuclear binding curve diagram that I showed you, you'll notice, not surprisingly, that iron sits at the top of the nuclear binding curve. And iron represents a boundary between fission and fusion. On this side of the periodic table, you can actually release energy by fusing small nuclei into bigger nuclei. But iron sits at the top of this curve, and that means if you try to fuse anything into iron to make it heavier, you start to go down in energy, and that means if you take iron and try to whack nuclei into it, instead of producing gamma rays, it will suck gamma rays out of the core of your star. A star can fuse iron into heavier elements in little splurts, but if it does so, it will suck energy from the core of the star, making it gravitationally unstable. This is why iron, I'm sorry?
I was just going to say, so iron's like the heaviest sustainable element that a star can produce.
That's right. It's the heaviest sustainable. Now keep in mind, Nathan, the crust of our planet is littered with all kinds of trace elements that are heavier than iron, right? Heard of gold before? Heard of silver before? Uranium? These are all elements that are heavier than iron. So when a star goes into its explosion phase of a supernova, there are little bits of shit bonker nuclear fusions that are happening all over the place that are not energy efficient. They actually cost the star gamma rays. But all of this stuff, anything heavier than iron, has a super low abundance in Earth's crust, right? And that's because all of these elements don't get mass produced sustainably, as you put it, inside the fusion reactions of stars. So I have a little slide, just so I'm not punching around the internet here. If you look at I've got the nuclear binding curve here. This is the abundance of elements relative to hydrogen. We've looked at this graph before. And you'll notice that after iron, the number density or the abundance of elements takes a sharp drop. So the idea is that all of these elements here, these are all produced by supernovae. They're not actually produced by stars, but they're produced in sort of the high energy, short-lived environment of a supernova where random nuclear reactions take place. And that means this element here, this is kind of the last, as you put it, sustainable. This is the last stop for nuclear fusion in high mass stars. So we can put this into our chart, and I think it would be a good idea for us to do that. And then I'll show you some fun photos before, oh, Riker, like it. Okay, so let's go back to our table here. We're getting towards the end of our lecture. Okay, so by the way, of course, these types of stars are called blue supergiants. And if you look at their location on the HR diagram, these are stars like Rigel or the very extreme bright stars, some of which we can see in our sky. And these fuse carbon.
Does the sun count as a very bright star in our sky?
Yes, the sun counts as a very bright star in our sky, but some of the bright stars, there are some blue supergiants out there, right? And when we look at a star like, if we look at a constellation like Orion, blue stars are always brighter than their surrounding white or reddish stars. But some of the stars in our sky are blue supergiants that are undergoing this extreme type of fusion. And I believe Rigel is one example of them. This is a blue supergiant. If you were to look at the interior layers of this star, you would see a complex Tootsie Roll-like structure that I've been describing. There's a nice picture of it in one of my slide shows. Where was that? Here. This is what the internal structure of a blue supergiant might look like. Forget about the fact that this picture is red. Doesn't matter. Actually, they can turn red if they, oh, you guys aren't seeing what I'm seeing. I don't see the share screen. Hold on, guys. I'm just managing the technology here. Share screen. This is what I was trying to show you. 98. If you could look at the interior of Rigel and drill down into its core, you would see this extremely complex layer of shell fusion, where you had layers of non-fusing hydrogen, hydrogen fusion, helium fusion. So this would probably be CNO cycle, triple alpha process. Then you'd start seeing your helium capture, and eventually you'd get to this big inert iron core. Thank you for that. That's very helpful. Okay. And eventually those stars would give up once they reach their limits for fusion. They will eventually explode in these sort of dramatic supernovae. Now, I don't know if I showed you this picture before. I think I did. But we recorded a legendary supernova in 1987A. Riker, can we get your arrow over here on this star? Okay, Riker, you think you can? Yeah. Okay, there we go. So this star was a sort of nobody star in the Large Magellanic Cloud, a dwarf elliptical galaxy surrounding the Milky Way. And in 1987, that star went from this to there when it underwent a dramatic Type 2 supernova. This is where the star has nothing left but a big iron nucleus, and the star stops fusion and just says, fuck it, and the whole star collapses on itself. The stars actually bounce off of the ball of neutrons and get propelled by the neutrinos into a very, very violent and dramatic explosion called the Type 2 supernova. They sometimes refer to this process as a neutron star bounce. And there's kind of a cool demo for this, which maybe I'll talk about next time. In the meantime, let's stop the share and let's fill out the rest of our chart here. So we go from carbon to elements like silicon and eventually to iron. And then our stars undergo a dramatic supernova. And it turns out that in our next class, we will learn there are different types of supernova. A high mass star supernova is a supernova of type 2. Now, the inner core of the star is going to end up in one of two states. It could end up as a neutron star.
Or a black hole.
That's right. So you get to choose one of these two possible. All stellar death involves two things. The outer envelope gets ejected outwards and the inner nuclear core collapses inwards. Honestly, this is some of the most interesting areas of astronomy, and I probably should have just jumped to neutron stars, black holes, and white dwarfs today. But I felt, class, and see if you can understand my logic before I end this lecture, I was concerned about jumping into these things without having made sure that you guys understood the background of the life cycles of stars. Whether or not you care about this is anyone's guess. But on Thursday's class, on our last class, we'll get to learn about the histories of white dwarfs, neutron stars, and black holes and their associated weirdnesses. So I kind of did this chart before, but I don't know. I felt like it needed more explanation. I may have been wrong about that, but this is how I remember it. Okay. So this is the end of our lecture, and now let's talk about what we're going to do for our laboratory exercise. We are going to study a class of stars called Cepheid variables. Cepheid variables are stars that lie on the instability strip. I have a picture of that here. The instability strip. Yeah. Stars like Polaris, the North Star, do not maintain hydrostatic equilibrium but they pull. Sorry, you guys can't see what I'm doing. Stars like Polaris occupy a region of the HR diagram called the instability strip. This is where stars are undergoing their helium to carbon fusion. And because of this thing called the helium valve, different stages of ionization of helium, these stars actually grow and shrink and pulsate. And we're going to be able to use this fact to our advantage to help estimate the distances to these stars. Now let's talk about what you're going to need for the lab, because I noticed somebody was asking that question in the chat log. We should have this under our Blackboard if we go to lab. Where are we here? Period luminosity relation. You guys can download your period luminosity lab here. Unfortunately, you're going to probably need the majority of this stuff, okay? You're going to need all this stuff. So I'm going to hit print on mine, and I want you guys to print yours or look it up. It's
What's the lab number?
lab number 16, okay? Oh, do you mean our internal class lab, or do you mean the lab number in the book?
In the book.
In the book, it's number 16. Internally, this is our
This is our 12th lab.
Our 12th and final lab. Although I think we skipped one in between. Okay, so should we take a few moments to drink some iced tea before we begin? Everyone?
For me.
Yes.
Okay. All right, so
Yeah, I
I'm
need to grab my
stop
charger.
the recording.